We proceed in this lecture to discuss the some aspects of the calculating the resistance of conductors, and this will sound very familiar because we use it all the time in circuits. So here we have an example. We have a conductor. This is here a piece of conductor. It has a surface area S. It has a length L. We apply a voltage difference V to its terminals. So this will force current to flow through the conductor from the positive terminal to the negative terminal, which means that electrons are actually flowing in the opposite direction. Remember, because here the voltage is positive here relative to here, the electric field, as I mentioned in the lecture, will be flowing from the positive higher potential to the lower potential. So electric field is flowing in this direction. Okay, which means that electrons will be drifting in the opposite direction. Now we'll make two assumptions here to simplify the analysis, which is valid in if you have a small conductor. This should work fine. We assume that the electric field here will not change with the distance, so electric field will be uniform inside with L. We'll assume also that we can that the current I is flowing here inside the conductor, the same current in the cross section, and the J will not depend on the distance. We can calculate the value of J in any cross section. So by making these assumptions, we can simplify things. We can say that the voltage V is equal to the integral of E dot dl, but E is constant. I can take it out and then integrate by dl will give you L. So this will give you E multiplied by L. So I can simply say that E is equal to V over I. The same thing for J. We know that the current is equal to the integral over the surface of J dot ds. But if J is constant in the cross section, I can take J out, and this will give you here J multiplied by the surface area, which we call it S, or it's called ds, delta S. It does not really matter. It is simply the surface area of this conductor. So now, and for this one, excuse me, for this one, delta S and S are identical. So if you see delta S, they are the same. So now what we do, we already calculated E as V over L. So the electric field intensity is equal to V over L. We know that the current density value, not vector really here, it's I over the area. It's called here delta S or S. It does not really make a big difference. So we know that J, the current density inside the conductor, and the electric field are related by the conductivity. So this one here is the current density. It's I over the area. And this one here is the electric field intensity, V over I, and they are related by sigma. Our target is to find the resistance of this conductor. Resistance, by definition, from circuit theory, it is V over I. So I'd like to get the ratio of V over I. And this V over I will give you, if you divide it, will give you L over sigma S. And this result, we know it from our from other courses, that a conductor, the longer a conductor is, the more the resistance is, and the wider it becomes, the less the resistance becomes. We can now take this 1 over sigma, which is the conductivity. We define something now called the resistivity. Resistivity, which is really the inverse of conductivity. It tells us how this conductor resists the flow of current. The higher the resistivity, the higher the resistance of this piece of conductor. So this is a very typical analysis where electromagnetics, under certain assumptions, give you the values or the equations we use in circuit theory. In general, for any conductor, you can calculate the resistance, and I will be showing some examples on that through the ratio between V between the two conductors and I, the current flowing between the two conductors. So to get the voltage difference between the two conductors, you have to do a line integral between the first conductor and the second conductor of the electric field. We agreed that the potential is the work done by the electric field in moving a unit charge from one point to another. And to get the current, you have to integrate over the appropriate surface of the current density. The current density vector is sigma E. Okay, so we agreed that in any material, electric field will create conduction current density. And this conduction current density, when it flows through a certain surface, it creates a current. So when you divide the voltage between the two conductors over the current between the two conductors, you get the resistance. Why did I did not include negative sign here? Because this quantity will be positive if I select the proper direction for ds. The current is flowing from the positive terminal to the negative terminal, so there is no need to include the negative sign here. That's the other part that we use all the time in our calculations in circuit theory, and maybe we don't know it originates in electromagnetics, is the concept of power dissipation. When you say power dissipation in a resistance or in any other situation, we know that the work done, we agreed that the work done is equal to force multiplying distance. In order to get the rate of change of work, which is power, it is simply force multiplying velocity. So in order to calculate the power dissipated in a certain volume, you have to integrate over this volume. You have to integrate what? Rho v dv will give you the charge of this infinitesimal volume. So when you multiply it by E, you get the force affecting this infinitesimal volume. And then you multiply by the velocity of this differential volume, so the velocity at which the charges are moving. So when you put all this together, this gives you the definition of the power. Remember that Q E dot D, where D is a distance, will give you work. But when you multiply by U, which is the rate of change of the distance, this will give you now power. We agreed earlier that J, the current density vector, is equal to rho V multiplying U. Rho V multiplying U will give you the current density vector. So now I can simply replace this one by this expression. And this expression is extremely important in electromagnetics. It tells you if you want to calculate the power dissipating in any volume, go at every point in this space, find the electric field, find the conduction current density, and take the dot product between them and integrate over the volume. So this one here, if you try to find the units, this one is in volt per meter, this one is in current per meter squared. So their product will be in watts per meter cubed. So it has units of power density. It is in watts per meter cubed. It's power per unit volume, and is equal to E dot J. We agreed as well that J is nothing but sigma E. So this will give you sigma E dot E, or sigma multiplied by modulus E squared. So now if I ask you to calculate the power dissipated in a conductor, this is what you have to do. Calculate the electric field at any point within this conductor, calculate the resultant current, which is equal to sigma E, do dot product between them, and integrate over the volume. Now where does this power go? It's actually converted to heat. So if you touch a conductor where there is a current flowing, you will see that it starts to heat a little bit. This is because of the conductivity and the corresponding heat. Now there is another expression we use in circuit theory. If I take this same expression here and I make some assumptions, I will assume that the electric field does not change in the cross section, and I will assume that J does not change along the length of the conductor. So I can replace this d volume, the volume integral, by a surface integral and a line integral. And the integral of E dl over the length of the conductor will give me the voltage difference across the conductor. The integral of J dot ds in the cross section of the conductor will give me the total current flowing through the conductor. So we end up with the power dissipated equal to VI. And this is an expression that we use all the time in circuit theory. We say if you have a resistance and the current through it is I, the voltage across it is V, then the power dissipating in it is VI, or I squared R, or V squared over R. It's exactly the same thing. It originated from electromagnetics with simple assumptions. We're able to take it to circuit theory. Last theoretical part I would like to mention this lecture is the concept of perfect conductor. Perfect conductor is a conductor where the conductivity is infinity. So you have infinite conductivity. So sigma here, sigma is equal to infinity. Sigma is equal to infinity. Huge conductivity. Now, if there is an external electric field applied to this conductor, if there is any field inside, Assume there is any field inside the conductor. What's going to happen is going to result in an infinite current. And infinite current will result in infinite loss, infinite heat. But of course there is nothing infinite here. Where would this infinite energy come from? What's going to happen is that if you have an external electric field applied, this external electric field will cause some positive charges to drift in its direction, some negative charges to drift against it. And you can see these charges now create their own electric field, an internal electric field EI. And this internal electric field will cancel the external electric field to give you zero electric field inside the conductor. So a perfect conductor cannot have any electric field inside. And because it does not have any electric field, then the D vector, which is the electric flux density vector, is zero, and its divergence is also zero. So there is no volumetric charge density inside. So now we know something very important about perfect conductors, and this is used very often, and we'll use it later when we talk about capacitors. A perfect conductor cannot have any electric field inside. It must have zero field. And the reason is, if it has any electric field inside, this will result in infinite current. And infinite current will result in infinite loss, which is not a physical thing. So what is happening? Charges will organize themselves on the surface in this way, positive charge in this direction, negative charge in this direction, to create internal field EI that cancels the external field. So the total field inside the conductor is the sum of the external field applied from the outside from other charges very far away, and the internal electric field caused by the conductor charges organizing themselves to cancel the total field inside, to cancel the applied electric field. So the total field is zero. Now, a perfect conductor is an equipotential surface. What does this mean? Every point inside the perfect conductor will have the same voltage. Why is that? Because if you have an electric field inside is equal to zero, then you can simply say that the integral, if you carry out the integral between any 2 points A and B, say the integral between A and B of E dot dl, this should give you the voltage difference, but this would be zero because there is no electric field inside. So every point is on a perfect conductor will have the same potential. Now let's take a look at a couple of examples. The first one, we have a coaxial cable. It has an inner radius A and an outer radius B, and it has a length of L. And between the two conductors, the inner and outer conductor, there is an insulator with conductivity sigma. Ideally, the conductivity should be zero here. If you have a perfect conductor, so perfect insulator, it should have zero conductivity. It should not conduct any current if an electric field is applied. But because in reality there is always some conductivity, even though it is low, we would like to find the conductance per unit length of this coaxial cable. And I will explain to you why we call it conductance, not resistance. So this is a coaxial cable we see. We have an inner conductor and we have an outer conductor. Okay. In reality, what we are aiming to do is to simply, if this is our coaxial cable here, and we would like to use it to transfer energy. So on the other side, I will have the other side here. I will connect a battery here on this side, and on the other side I will connect a resistor. Okay. Actually, this figure, maybe I should it actually to be more accurate. So I will simply draw, but it has to be relative to the ground. So if I want to make it accurate, I have to draw it through the external conductor, because the current will have to flow in the internal inside conductor this way, and it has to come back through the external conductor. So the circuit to be closed. Now the problem is the material filling the gap between the two conductors here is not perfect. So the current is not only going to be flowing inside the inner conductor and coming back from the outer conductor. No, there will be also a current flowing radially from the inner conductor to the outer conductor, because these two conductors have a voltage difference between them. So and this is really undesired current. This is a leakage current. We don't want usually to have this current, but it does exist because of the finite of the insulator here does not have infinite resistivity. It has actually some conductivity. It It has some conductivity. The conductivity should ideally be 0. So now how do you solve this problem? We can try to look at it from the top view. So if we someone take a look here at this conductor from the top, what you're going to be seeing, you see the figure to the left, you see the inner conductor, you see the outer conductor, and you see current flowing from the inner conductor, outer conductor. This current is weak, is very weak relative to the current flowing inside the conductor, but we want to calculate it. So if I call this current I, and it's flowing radially, and as you can see, it must be symmetric, so it is in the radial direction, and it only should vary with ρ. If I want to carry, the current actually does not vary, the current is the same. What will vary is the current density. If I want to get the current density, I have to divide this current I by the surface area of this surface at any radius ρ. So J here will be a function of ρ. What is this surface area? This is the external surface area of a cylinder. Is equal to 2 pi ρ multiplied by the length of the cylinder. Now, if I know the current density flowing here, then I know the electric field, because they are related by the conductivity. And if I know the electric field, I can calculate the voltage difference between here, this conductor, and this conductor in terms of the current. And I can get the ratio V to I. This is what I'm looking for. I would like to get the ratio V to the leakage current I. And this is what will give me the conductance. So the steps will be as follows. I know the current. I will assume a current I flowing from the inner conductor to the outer conductor. I will calculate from it the current density through a surface. And this, of course, by changing the radius, you can see the current density will become different. By knowing the current density J ρ, I can get the electric field flowing in the radial direction. There is an electric field from the positive conductor to the negative conductor, or to the one that's grounded. By knowing the current, I can do an integral from A to B to get the potential difference, and then I can divide V to I to get the conductance. This is how things will go. We divide first the current I, which I assumed it's flowing. I don't need its value. I just assume that the current I. Then for any radius ρ, this is the value of the current density, I over 2 pi ρ L. I assume here a cylinder to have a length of L, or the conductor to have a length of L, and ρ is the radius. So J is in the ρ direction, and if I know the conduction current density J, I know the electric field, because they are related through the conductivity of the insulator. Ideally, sigma should be 0, and I shouldn't have any conduction current, but we do have some conductivity. So J is equal to sigma E. I know what is J. I can get E. I divide J by sigma. So this is the electric field flowing from the inner conductor to the outer conductor in the radial direction. Now, if I want to get the voltage difference, my target here is to get the ratio between the voltage difference between the two conductors divided by the current to get their conductance, or the equivalent resistance here in this case. So I can simply say the voltage difference between the positive conductor to the negative conductor is the integral from the inner conductor to the outer conductor of E dot dl. It is the work done by the electric field. Of course here, because this one has only a ρ component, dl will have only the component d ρ, a ρ in cylindrical coordinates. I will neglect the phi and z components. I can take all the components out except 1 over ρ. The integral of 1 over ρ will give me ln ρ. You put upper limit minus lower limit, you get ln b over a. Now we know that the voltage difference between the inner conductor and the outer conductor is given by this value in terms of the leakage current. I'm looking for the conductance, which is the ratio between the leakage current to the voltage difference. Of course, ideally, there should be no leakage current. But in reality, there is always some leakage current. You divide I by VA minus VB, you get this expression. And of course, because I'm looking for the conductance per unit length, I will divide G by L. By the assumed length, I will get the conductance per unit length. And this parameter is very important when you study transmission line theory. So now you can see this conductance will be 0 if the conductivity is 0, which is expected. So there should be no current flowing from the inner conductor to the outer conductor, but in reality there is always some tiny current flow. Now let's take a look at a second example. We would like to calculate the power dissipated within a resistor that has a uniform conductivity sigma. We assume that the conductor has a voltage difference between its terminals of delta V, and there is a current passing through it of I. So again, this will look more like a circuit theory exercise, but it's very related to electromagnetics. So here I will make an assumption that the conductor has a cylindrical shape. That's the easiest way we can handle it. There is a current flowing from the positive terminal to the negative terminal, so the current is flowing in this direction. And if you want to get the power dissipated within this conductor, you have to integrate over the volume of J dot E, the volume. What is J? J is equal to the current divided by the cross section. And here I will assume that J is uniform on the cross section, just to simplify the analysis. So J is equal to I over delta S. And also I will assume here that the voltage difference is equal to E delta L, so E multiplied by the length. Or I call it here D, it does not really matter. It's E multiplied by DL, so I will assume that E is uniform along the length. So two assumptions I made to simplify the analysis. I assume that J, the current, is uniform on the cross section, so J does not depend on S, does not vary from one point to another here in the cross section. And I will assume that E does not vary from one point to another in the length direction. So it's the same E. So by doing these two assumptions, and J is flowing in the Z direction, E is in the Z direction, I can simply say that J is equal to I over the area, pi A squared in the Z direction. I can assume that E is equal to the voltage difference divided by the length of that conductor, which here I called it D. So here it's called D. This is not A, this is D. Okay? So this parameter here is really D, the length of the conductor. And I will integrate this over the volume of the conductor. I have a conductor of height D, of cross section A, of radius A, and then I will integrate over the whole volume from 0 to A, from 0 to D. I will integrate phi from 0 up to 2 pi. The unit, of course, the volume element for cylindrical coordinates is rho d phi dz. Now things start to simplify because the integral over phi will give you 2 pi, so I take this one out. Then these are all constants. There is no function of phi or z. The integral from 0 to d of dz will give you d, so I take that one out. The integral of rho d rho will give you rho squared over 2. I substitute for the upper limit, I get a squared over 2. This is all multiplying I over pi a squared, multiplying delta v over d. Notice d will cancel with d. This term, 2 pi multiplied by a squared over 2 will cancel with by a squared, and the answer is I delta v. This is the answer that we get from circuit theory, that the voltage dissipated across a resistor is equal to the current multiplied by the voltage difference across that resistor, which is the same one. So electromagnetics, under certain assumptions, will lead to the circuit theory expressions we use all the time.